So let us conclude the lecture number 3. So this lecture is actually the lecture that we should have in the class on Thursday next week. It means the coming week. I'm recording it quite early, like one week in advance. So I hope everything will be ready, and homework and other things, so you will basically have all the materials ready to review and to learn the topic. So let me write down the problem. We'll give you several examples of the possible problems. So put it like this: problem, and the problem is the following: find the Taylor expansion of the indicated function f of z at the specified point z0, you can say around the specified point z0, and our example will be just the function f of z equals, and this will be z divided by z squared minus 2z plus 5 at the point z0 is equal to 1. So let me indicate. So in this case, of course, we are looking for power series expansion. So let me write it down. What we are doing, we are looking for this power series expansion, which will be of this particular form. So this is going to be an, and this one is going to be z minus 1 to the power n. So those will be the powers z minus 1 to the power n. And that is important. So let me indicate solution. So let's go do the solution. And let's begin. So in order to do it, so we will first of all notice that z squared minus 2z plus 5 is equal to z minus 1 squared plus 4. So you can see here, of course, I already have this particular good form. That means z minus 1 is actually, we're lucky, we have it here. So now I can rewrite the function. So let me rewrite the function, and I will just continue writing it in the one sequence. I'll write it down like this. I replace bottom by z squared minus 2z plus 5, and this is z. So what do? I put here z minus 1 plus 1. Yes, because I want exactly this powers to be. And then I have here z squared, z minus 1 squared plus 4. And then I split it into the two fractions, z minus 1, and then I put here 4 plus z minus 1 squared, and then plus, and the second fraction will be exactly the same, with the same denominator. And now I look at this fraction and say, okay, let's pull out 4. So I put here 1, 4, and write it down. This will be like a z minus 1, and here will be 1 plus, and this will be z minus 1 squared divided by 4 plus, and that one is equal to exactly the same, so put here 1, 4, this will be 1, and this is z minus 1 square divided by 4. And then I say, wow, I have here the something that looks like this, 1 plus q. So you see, this is my q in both cases. This is the q, this is the same thing. And that I have seen, we already know that this will give us the geometric series with the minus 1. So this will make a q to the power n, and I can use it. So I will use it, so I will write it down just simply. This is 1, 4, maybe. Right. Now z minus 1 divided by 4, and here that's exactly, you see, that's exactly this expression, so I can write it down. Infinite sum n is equal to 0 to infinity z minus 1 to the power n divided by 4 to the power n, and the same here, 1/4, and this will be n is equal 0 to infinity, and this is z minus 1 to the power n, 4 to the power n. Now we can simplify it, namely you can see that I can enter with the n is equal, I forgot, minus 1 to the power n, and minus 1 to the power n. Okay, now it is correct, now it is correct, now it is correct. So this is equal to 0 to infinity, and what do I have? So first one is again minus 1 to the power n, and this is z minus 1. Of course it's not correct, it's not correct. It has to be 2, because we have here square. So let me look again. Yes, this time is correct, so everything, we have to be careful, we have to concentrate. The software is not working very well today, so it makes me a little nervous. So plus 1, this is that form, and the second one is again the n is equal to 0 to infinity, minus 1 to n. As you know, if you use the free software, you don't always get the things smooth. And so I tried to record this presentation before, and I couldn't go through it because the pen stopped working. It stopped working, so I could not do anything. So now I think it's okay. So of course I will simplify it in a moment. First I need to notice that this is odd number, this one is even number, so the powers do not repeat, and that means this is basically this could be considered as the answer. It gives you the power series, 2 power series, which actually can be, let's say, can be written as a 1 power series. Maybe I can write it down. So let me write it down like this. This is a power series. Unfortunately, it's kind of difficult to put it in other way than that way. So you have to indicate what is z minus z 0 to the power n. So that means n can be either even or odd, and you can indicate that this an in this case it is equal, and we put it like this, minus 1 to the power k divided by 4 to the power k plus 1 if n is equal to 2k plus 1. That means I need to change it to the power. So instead you can think about this is k and this is 2k plus 1, so that becomes your n. And this is for odd, and for even it will be just simply minus 1 to the power k, and this will be 4 to the power k plus 1 if n is equal to k for odd. Or you can just simply write your answer using this particular form, namely put it like this, minus 1 to the power n, and this will be 1 divided by 4 plus 1, and then what is left it is just left the even powers and the odd powers in the inside of the bracket. And this would be your answer. This would be your answer. So this is the answer. So let's go to another simple problem. I do this problem just for one purpose, just to show you that it is also possible. So the B is that your function f of z is equal to 1 plus z plus z2 plus z3. That such an elementary function, elementary simple function, can actually cause a little problems if you put here, for example, a given a point which is not exactly 0, because this would be a nice power series, you know. Polynomial is a power series. Polynomial is just a finite power series. And here we have a polynomial of third degree, and I want to have this polynomial expressed in the powers again, in the powers of, let's put it clearly, z minus I. So these are the powers that I want. So in such a case, in order to do it correctly, I will remember that in this case, the power series can be easily determined, because I know that if you have here this f of z, so let's write it down, it will have only the power series like this. No, maybe I don't need this one. Or maybe write it down. Right? So this will be like a0 plus a1 z minus I plus a2 z minus I square. Of course, this is polynomial of third degree, so there will be only z minus I cubed. And the thing that we are observing is that these coefficients we already know. This was written in the Taylor expansion formula, that basically this ak is nothing else than the derivative, k derivative, of the function z at the point I divided by k factorial. So that's the trick. So let's do it. So let's compute it. F of z is equal 1 plus z squared plus z cubed. F prime of z is equal z plus 2z plus 3z squared. And then you have here f double prime of z is equal 1 plus that's 1. So this is wrong. So let me write it down. This is 1. Then this will be equal to 2 plus 6z, and the third derivative of z will be just equal to 6. So now we just compute f of I, and you are getting, f of I, it is 1 plus I minus 1 minus I equals 0. Good. F prime of I is equal 1 plus 2I minus 3, so this is equal minus 2 plus 2I. And then I have here second derivative at I is equal to the 2 plus 6I, and the third derivative of this function at the point I is equal to 6. And then I can write the answer, and using this formula here, it will be just simply equal f of z is equal, so a0 is 0, so there is nothing to write, and then I write it down. This is minus 2 plus 2I divided by 1 factorial, and this is z minus I, and then you have plus, and the second one is this one, so this will be 2 plus 6I divided by 2 factorial, and this will be z minus I square, and this will be 6 divided by 3 factorial, z minus I, and this will be cube. So we have it. So maybe let's simplify it. So we are getting this is minus 2 plus 2i times z minus I, and the second one will be 1 plus 3i, and this is z minus I square, and that one will be just simply z minus I cube, and this is our answer. This is our answer. So I think this is enough, and maybe let's do one more problem. Let's say make the things a little more, let's say, exciting. You know, could you know? Those are very easy problems, as you saw. So let's see something maybe more complicated. So I put here like this: f of z is just a principal value of the logarithm, and I put here 1 minus z, and since I want to have it more complicated, I put here square. So this is a logarithm square. And you notice this is exactly one of these examples that we did in the previous lecture. So we already know that in such a case, okay, z0 here will be 0, so just for simplicity. So we did this example, so you can see that in our case that particular logarithm, this is principal logarithm 1 minus z, can be written as minus, and what do I get here? N is equal 0 to infinity, no, not 0 to infinity, 1, okay, 0 to infinity, and this will be z to the power n plus 1 divided by n plus 1, which can be written like a minus, and here we are having here, this is n is equal to 1 to infinity, and this will be zn divided by n. So this will be our logarithm. So let me do the solution. So I start the solution. And in here, of course, that means this f of z turns out that this is a product of two series. Here, of course, we have here this minus 1, but since we have here this square, so I can just forget this minus 1 and just simply write that this is equal to sigma, this is n is equal to 1 to infinity, and this is zn divided by n times z to the power n is equal to 1 to infinity, zn divided by n. And in order to be, let's say, to show how it actually, what kind of the situation we are getting here, so of course we will start with 1, so we are getting z plus z square over 2 plus z cube over 3 plus z 4 over 4, etc. And you will be multiplying this series by exactly the same series, so you can immediately recognize that the powers, this is very similar, like multiplying two brackets by itself. So of course in such a case you'll see that the first power starts with this will be the power number, this will be power number 2, and 10. Look what I'm getting. Then you are getting power 3, so that means you are getting it by multiplying power 1, so that means that one, and then you multiply by 2 power, and vice versa, So I will just notice that this is twice the same, so I'll put it like this. This will be 2 times, and I'm getting here that this will be like this times 1/2, right? 1/2, and that one will be times z cube. Am I right? Let me check it. So 1/2 times this and this, yes. And then you are getting another one. This will be z4, etc. But that's not a precise formula. This is not a really precise formula. We should write it down correctly. We should not write it down properly. So what actually I will be getting? I will be getting that this will be the product of two series. So this will be starting with the power 2 going to the infinity, and this will be like a Cn, and this will be z to the power n, where Cn I can rewrite it. This will be equal. So this is k starts at 1, k0 is 0, so, and it goes to n minus 1, probably, because you will find out that there is no k0, so there will be no correspondence, and then you have here 1 over k times 1 over n minus k. And then I look at this expression and say, okay, I can actually compute this particular sum here, that maybe let's see, try to erase something. So this sum I can compute here, make it like this, separated, so this will be equal, look, I take this one, 1 over n out, and here I can rewrite it, k is equal 1 to n minus 1, and this would be 1 over k plus 1 over n minus k. But that is interesting sum. Look, here if you write these two sums separately, so you will be getting this is 1 over n, and this is equal, k is equal 1 to n minus 1, this is 1 over k, plus 1 over n, and that sum is k is equal 1 to n minus 1, and that one is n minus k. So look, this sum starts this sum starts like 1 plus 1 over 2 plus, okay, plus 1 over n minus k, 1, and that one is going opposite direction, 1 n minus 1, blah blah blah, plus 1 over 2 plus 1 over 1. So this is exactly the same twice. So I just simply write it down. This is equal to n, and that means 2, and this is k is equal 1 to n minus 1 to n minus 1, 1 over k, to 1 over k. And now I can write the answer. So in such a case, we are getting that this series is equal, and let me write it down. This series is equal, and I write it down as a formula, n is equal to the infinity. I put here 2, and I put here this sum, k is equal 1 to n minus 1, 1 over k. And this is like a part of the harmonic series, as you notice. And then I put the n over the z to the power n divided by n. It has kind of a connection with this logarithm. You see the logarithm here. I see it's like the same form. So I put it the same form. Of course, I should mention that symbol here, that this part of the harmonic series is also used. They use especially in all kinds of. They use this notation, H, capital H, they call it like a Heaviside numbers, something like that. N minus 1, because this is from 1 to n minus 1, so that number is like denoted by H, n minus 1. So if I use this symbol, then I will get that this will be 2h n minus 1 zn divided by n, and I got these things now. So we did a couple of these examples. So in order to cover properly all the material that is needed, so let me specify several important, let's say, additional properties. So I put it like this, just simply maybe properties of analytic functions, So we start with, okay, suppose, let's say, with the setting, suppose U is contained in C, and F from U to C is an analytic function and assume that this analytic function is not equal identically to 0, so I've crossed out the 0, analytic function f is such that there exists, such that maybe forget exists, such that f of z0 is equal to 0. Can you see it? Z0 is equal to 0 for some Z0 belonging to U. So in such a situation, when you have here this particular situation, function as analytic function is not 0, but at certain point it takes the value 0. So in such a case, we will say that Z0 is a 0, and we call it 0 of the function of f of z. This means f applied on that point is 0, so we call it 0 of the function f of z. Kind of stupid, but that's how they do it. So, and now, of course, what does it mean? On the other hand, we have the power series expansion. So consider power series expansion. And this power series expansion at the point z0, so that means your f of z will be equal, and let me spread it. This will be a0, and then I have here a1, z minus z0, then plus, and this will be a m minus 1, z minus z0, m minus 1, and then I go further, plus a m, z minus z0 to the power m, and then blah blah blah, a lot of all the others. So what does it mean that f z0 is equal to 0? So look, if you plug everywhere z equals to z0, you're getting 0, 0, 0. So that means a0 must be 0. So because that is the value at a0. So this must be value at a0. So here we have a 0. So if this one is 0, then maybe there are other zeros. Maybe this one is 0, maybe this one is 0, and this one maybe not 0. They cannot be all zeros, because in such a case, what you will get that your function is identically 0. Because all the coefficients are 0, so function is 0. So there is, no, that would contradict our assumption. So there will be, of course, the last not zero coefficient, and then there will be the first m coefficient. So if am different than 0, first non-zero coefficient, then in such a situation, then the 0 z0 is said to be of multiplicity m. Interesting. So if the 0 is of multiplicity m, well, how to find out that this is a 0 of multiplicity? So now you say like this, what does it mean, the multiplicity? All the coefficients, m minus 1 including, are 0. The first one that is non-zero is am. So what is ak? Remember, an in general is the n derivative at z0 divided by n factorial. So if this is equal to 0, then this is equivalent that fn at z0 is equal to 0. So that means put Hitler like a proposition. F of z has a 0 z0 of multiplicity maybe let me try to erase it. Has z0 as a 0 of multiplicity z0 and if and only if the following situation is satisfied. F at z0 must be equal to 0. And then you have here f prime at z0 must be equal to 0. And then you go to up to n minus 1, m minus m-1, always so ugly, m-1 at z0 is equal to 0, but fm derivative at z0 is different than 0. So this is how we recognize the let's say I'll say it. This is how we recognize the multiplicity of the 0. So that's the one thing. So let's make an example, maybe something simple. Let me see if what would I do? Okay, let me do this example. Determine all zeros of the function f of z is equal, I put here sine square of z and their multiplicity. So let's do it. So maybe solution. We have here immediate observation that sine square of z is equal to 0 if and only if sine of z is equal to 0, and this is if and only if z, put here like this, z0, so this will be equal to, so this is pi k, where k is equal 0, 1, plus minus 2, etc. So there are infinitely many zeros. So the first part, determine 0, easy. Let's take any of those z zeros, so let's say, and compute and find out what is the, so you have here order of the zeros. So this will be the 0. So which one is it? That one. This is my the 0, and I know already that this is true. So now let's compute the first derivative. So we have here that phi prime is equal to 2 sine z cosine z, and this is also, this one is equal to 2, becomes sine of 2z. So then you have here prime at z0 is equal sine of 2z0, so recall it, this is sine of 2 pi k, and that of course is 0. So that is, so let's go to the third derivative, the second derivative. So you have here z0 is equal to, the second derivative is equal, so this will be 2 cosine, and what do I get here? 2z0, and then of course plug it in, and you are getting 2 cosine 2 pi k, and of course the cosine of 2 pi k is 1, so you are getting 1, and this is not equal to 0, so you are getting here that this is the second derivative is non-zero, so the z0 equals k pi is 0, 0 of multiplicity 2. So that's how you will be doing it. So now let's go back to our functions, to our general situation. So notice that if you have here the function f of z, and now you have here z0, 0 of multiplicity m, so that means your power, you can write maybe of your power series like this, n is equal to 0 to infinity, a n and z minus z0 to the power n, actually as a power series that starts with the mth power. This will be z minus z0, and then this is power m plus a m plus 1, and this will be z minus z0 m plus 1, and others. So this, in such a case I can do the following. Let me do it like this. So in such a case we have here that this power series starts with m is equal, n is equal to m to the infinity, and this is a n z minus z0 to the power n. I can pull out this power, mth power, out, and then I will get here the m is equal to, again, m, and this is infinity, and this will be a n, and this is z minus z0 to the power n minus m. If you rewrite it correctly, so let's say long series, so you will find out that this starts with an, then you have am plus 1 z minus 0, then you have am plus 2 z minus z0 square, and so on. So we go here and we say, why not to denote that this as a function g of z? That's a power series, and that one is not equal to 0. So that means we are getting the g at z0 is equal am, and that one is not equal to 0 because 0 was of multiplicity m, so that one is not 0. So in a certain way you can see that my function f of z can be represented, can be written in the neighborhood of z minus z0 to the power m and g of z in a neighborhood of z0. In a neighborhood of z0 can be written by this formula. Since, no, look here, look. Since g of z0 is not equal to 0, by continuity, of g, that's analytic function, so it's continuous, there exists an epsilon larger than 0 such that for all z's, such that z minus z0 smaller equal than epsilon, I put here smaller equal, we have that g of z is not equal to 0. So what did we get? So we got that there exists a small neighborhood here, this is z0, this is a epsilon, and my function in this neighborhood can be written like this: f of z is equal z minus z0 to the power m, and this is g of z, and that one is not equal to 0. Okay, something is 0. This is not equal to 0. So that means if you look at this equation, f of z is equal to 0, you will get that there is only one solution in this disk, so this is my b epsilon 0. There is only one solution. This is the only solution to this equation, only solution. And that means that if function is not identically 0, let's put it like conclusion. If the analytical function, if n analytic function f of z, f is different than 0, right? If an analytic function f of 0 has, I should not write it, an analytic function without if, an analytic function f of z admits only zeros that are isolated. Isolated. This is isolated. These zeros are all isolated. That means in a neighborhood of this zero, like a small epsilon, there are no other zeros. They can be separated by a barrier, by social distancing. The zeros have social distancing. Zeros won't get virus. The COVID will not hit them because they keep social distancing. Distancing from other zeros. And that of course brings us to the following conclusion. I hope I'm sick. I'm not sick, No, I'm coughing. No fever. I'm still there. Don't count on it. I'm not going to fall into this trap. Okay, so put it like this: conclusion. If f, and put it like this, f1 and f2 from u to c are two analytic functions such that they coincide on a set having an accumulation or limit point in U, then they are identically the same. They are identically equal. So they are exactly the same. There are no difference. That means for every z belonging to U, f1 of z is equal to f2 of z. And how do we do it? Look, actually, let's see. Let's do the little proof. Put the function f of z is equal f1 of z minus f2 of z. So notice that f of z is analytic. Yes. And then, if f of z is equal to 0, that implies this is if and only if f1 of z is equal to f2 of z. So now, the functions coincide on a set with a limit point. And what does it mean, limit point? Limit point, we have here like we have here like S0, and then there it coincides here, coincides here, coincides here, coincides here, coincides here, and of course coincides there. So you see, this limit point is not isolated, because you take any neighborhood, you have other points where from this sequence, from other points where these two functions coincide. So that means f of z has a 0 that is not isolated. So in that case, of course, this is 0 that is not isolated. So that means simply that it cannot be non-zero function. That means it must be a 0 function. So that means f must be a cannot be non-zero. So let's say must be a 0 function. Come on. Must be identically 0, and this is exactly that these two functions are equal. So that means that. Okay, we survived. That's the first week, the end of the first week of teaching. You should look into the classes that I'm presenting as a hint for all the assignment problems that will follow. Examination problems will follow, and these people who basically master the solving of problems in the game. Let me point out that I was using, I don't have it here around, the KGB book with the problems for some of those problems that I solved today. So you look inside the book for more problems and try to check if you are able to beat the KGB standards. Okay, so thank you. Okay, bye.